Good morning, friends. I am Dr. Dwivedhi, professor from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. I am in the process of giving lecture on aircraft stability and control. Today, I am in the lecture number 42, tutorial number 2. In this, I am going to discuss some numerical problems related to the longitudinal static stability. So, in this lecture, following topics to be covered in this lecture. Basic problems will be solved related to coefficient of lift and aspect ratio in cruise flight. So, in this, I am going to discuss these topics. In the previous lecture, that is tutorial number 1, I have discussed some very simple and basic problems related to the aircraft longitudinal static stability and what is the tendency and how we can say that aircraft is longitudinal static stable. I have given some 4 models of aircraft and how we can say that this model is statically stable. In this lecture, I am going to proceed with some new topics like this. So now my problem number 1, you can see that for an airplane flying at altitude with trim condition, it is CL1 and velocity V1 and angle of attack alpha 1. Now, airplane wants to fly at new coefficient of lift CL2, which is greater than the previous CL1. Means CL2 is greater than CL1. What will be the relation with V1 and V2? So here we can say that CL1 of first aircraft is given, the velocity of the first aircraft is given and it is flying at some angle of attack alpha 1 is also given. Another aircraft, which is aircraft number 2, which is having coefficient of lift CL2. This CL2 is greater than the CL1. Means this the second aircraft is flying with a high coefficient of lift. The question is, what will be the relation between two velocity, that is velocity 1 and velocity 2? We know that for the cruise flight, here CL1 is equal to 2W rho V1 square. We know that lift is equal to half rho V square S into CL. For the cruise condition, lift will be is equal to weight. So, CL1 here will be 2W divided by rho V square S. So, here I have not put here S, we can put here S, but S is constant. So, we have removed here. So, here we can say that for the CL1, it is 2W rho V1 square S, and for the CL2, 2W rho V2 square. We know that, so CL2 is equal to CL1 into V1 square by V2 square. Okay, so CL2 is equal to CL1 V1 square by V2 square. Since we know that CL2 is greater than CL1. So, V2 by V1, so here V2 by V1 is equal to under root CL1 by CL2. So, here we can say that if the CL2 is high, aircraft has to fly at less speed. So, this V2 is lesser speed. So, if you want to fly at a higher coefficient of lift, this higher coefficient of lift is used during landing and takeoff. So, during landing and takeoff, especially during landing, we need much higher coefficient of lift. You can see the birds and all. When they are landing, they are opening their wing to increase the coefficient of lift. You can see the aircraft. We are using the flaps. We are extending the flap downwards so that the coefficient of lift during landing is increased. This increase of coefficient of lift because during landing we cannot go very high speed. If we go very high speed, aircraft may overrun the runway and aircraft may be in trouble. So during landing especially, we make V2 is very less comparing to the V1 because that time we need more coefficient of lift. So to have, once we increase the CL, we should decrease the speed of the aircraft, making angle of attack constant. That we have to understand. So this is the first problem. Hope you have understood, and it will be very useful for understanding the basic concept of lift and coefficient of lift, in which condition we should have more CL and in which condition we should have less CL. So during landing, aircraft should not go very high speed. So how we will get the to sustain, to counter the weight? To counter the weight, we need to flap down. Once we putting the flap down, lift coefficient is increased and also drag coefficient is also increased. This increase in the drag coefficient will reduce the runway also. Okay, so that is the purpose of this thing. Now I have another very simple, but it is very tricky. Lot of mistakes are done during conversion from radian to degree and degree to radian. In our this total aircraft stability and control course, everywhere conversions are there. But I find that lot of people are doing a lot of mistakes. They are not able to convert properly. So here is small examples is given. The lift slope curve for an aircraft is given. CL alpha is equal to 0.09 per degree. What is the value of CL alpha in radian? So lift slope curve like this, CL, this is the alpha and this is the CL. So it is a positive. CL alpha is given positive. So I am making like this. So here this is the slope and this slope is 0.09. This is dCl by d alpha. It is a positive, means going upward. We want to convert this thing in radian. It is in degree. So how to convert in degree? So we know that to convert from degree to per radian, we need to multiply by 180 by pi. We know that pi radian is equal to 180 degree. So that pi radian is equal to 180 degree. So 0.09 into 180 by pi or 57.3. So 0.09 into 57.3, you will get 5.156 per radian. So if you want to convert from degree to radian, we have to multiply by 57.3 or 180 by pi radian. It is very important that whenever you solve the numericals, you should understand wherever degree and radians are there, take very much caution and then you apply this thing. Otherwise, your full hard work will go in vain. Now I am in the problem number 3. An airplane with wing span 2 meters and wing area is 0.6 meter square. Calculate the aspect ratio of the wing. You know that aspect ratio is very important parameters for any aircraft, for any birds and for any insects or any avians. The aspect ratio is one of the very important parameter because it will give the efficiency also. If you have the more aspect ratio, aircraft will be having less drag. But we cannot keep the aspect ratio as we want because there are some structural issues, bending moments, and these things will be generated. Then how much maximize the aspect ratio? You can see how we can identify that which aircraft has got more aspect ratio? Just you can see the aspect ratio. We know that the aspect ratio is one of the important geometrical parameter for the aircraft stability and performance analysis. The aspect ratio, it is also represented by AR. AR is equal to span square divided by area of the wing. So span is represented by B. So B square by S. But if you have the rectangular wing, just you see, if you have the rectangular wing like this is the chord C, this is the chord, and this is the span B. So the aspect ratio is B square, means span square divided by area of the wing. So in this question, B is given 2 meter and the area is given 0.6 meter. So here B square, 2 square, 4 divided by 0.6. So you will get 6.66. This is the aspect ratio of the wing. But how you can identify that which aircraft? By seeing the aircraft, how you can identify that this aircraft has got more aspect ratio? So if you see from the top view, 2 aircrafts are there. This is the 1 and this is the 2. This is the C, this is the B, this is the C, and this is the B. So by seeing this, we can see that the aircraft number 2, this one, has more aspect ratio because B is same but C is less. So if C is less, we scored, so this area will be reduced. So this here, B square divided by B into C. So B and B is cancelled. If C is less, the value of aspect ratio will be more. So by seeing these 2 aircraft, we can directly say that aircraft number 2 has more aspect ratio and aircraft number 1 has less aspect ratio, and this is the more aspect ratio. So from here onwards, you can say that the aircraft number 2 will have less drag, aircraft number 2 will have better gliding capability, aircraft number 2 will have landing and other parameters very efficiently comparing to the aircraft number 1. So this aspect ratio plays a very important role for aircraft performance. Next question is very important. This is the problem number 4, and this needs lot of introspection of the theory which we have already studied during our module number 1. In this, we can say that consider the airplane with following given parameters. Weight of the airplane, W is 25,000 kg. Cruise speed, V, 130 meter per second. Area of the wing, S, is equal to 60 meter square. Density of the air is 0.85 kg per meter cube. Aspect ratio 5. The CG location and the AC location are in the same point at 0.3 of the chord. Neutral point is given XNP 0.52 of the chord. CMAC, coefficient of moment of the aircraft, is minus 0.1. Coefficient of lift of the wing is 4.584 per radian. You should understand here per radian is given. We should be very much cautious because here alpha and IW all are in the degrees and here it is in radian. So we have to have a same unit. So we have to convert as and when required. This alpha 0 lift means it is at 0 angle of attack. When the lift is 0, it is angle of attack is -2, means it is a cambered airfoil. The wing has cambered airfoil. This is shows that because at -2 you are getting alpha 0. Alpha 0 means the lift is 0 at minus 2 degree angle of attack. IW is a wing setting angle and IT is a tail setting angle. Tail setting angle is also minus. This indicates that the nose of the tail is towards bottom, 2 degree towards the bottom. NT is a dynamic efficiency 0.8 and this is the horizontal tail ratio is 0.45. E is equal to 1, tau is equal to 0.54 and deflection E maximum is plus minus 20 degree, means elevator deflection. So what we have to find out? We have to find out lift coefficient for the cruise. Lift coefficient for the cruise. Then downwash angle, epsilon naught. Coefficient of movement of the wing at 0 angle of attack, that is called Cm naught W. Value of Cm naught, value of Cm delta E, it is also called the control power. Static margin and delta E required for cruise flight. So these 7 items we are going to solve now and hope you will understand, and it is very simple to handle. Only you should take care of angles, degree and radian. If you are able to handle this thing, everything we have to put the equations and we have to solve the problems. So in this, we have to use these formulas which we have already discussed in our class lectures. 1, 2, 3, 4. These 4 equations will be used here. Cm naught is equal to Cm naught W, wing. W is stand for wings, plus W Cm naught, Fs means fuselage, plus Cm naught T. Here we will not be considering fuselage. We will be only considering wing and tail. Now Cm naught tail is equal to neta VH CL alpha T epsilon naught plus IW minus IT, and CMW means wing is equal to Cm AC plus CL naught W XCG minus XCG and XAC, and epsilon naught, that is downwash angle, is equal to 2 CL naught W divided by pi aspect ratio of the wing. So here a very simple procedure. This Cm naught will go, first we have to find out the Cm naught W and then Cm naught T, and this Cm naught W we will use this equation. To find this Cm naught T we will use this equation. To find the downwash angle we will use this equation. Very simple. It is just, so first question, how to find the lift coefficient CL for the cruise flight. Just in the previous I have explained that lift is equal to half rho V square S CL. If it is a cruise, then lift is equal to weight. So CL will be weight divided by half rho V square S. Here it is given 25,000 weight into 9.81 divided by 0.5. Rho is given 0.85 kg per meter cube. Velocity is 130 meter square into S is equal to 60 meter square. Then we will get 0.569. So the CL of the cruise is 0.6. This is very high. Normally aircraft will not fly coefficient of lift at 0.6. Okay, so this is not a practical solution for the aircraft. For the cruise flight, your CL should be 0.2, 0.3. That is the best option. Okay, but however, as per the given numerical value, we have find out this coefficient of lift. Okay, but in the real scenario, aircraft will never fly in cruise 0.6 CL. That you have to understand that at what condition your aircraft is flying in which coefficient of lift. Now second problem is we have to find out the downwash angle epsilon naught. So epsilon naught is equal to 2 CL alpha W into alpha naught L divided by pi aspect ratio. So here 2 into 4.584 into alpha naught is given 2 degree divided by 5 aspect ratio into pi. So here we will get 0.0203 radian. This radian we have to convert to the degree because other parameters are given in degree. So we have to multiply by 57.3. So we will get 1.16 degree. So this is the downwards. So means your wind is going like this, and after touching the wing, it is 1.16. It is going down. That is the meaning of downwards. So wind is not going straight. After touching the wing, when it is reaching to the tail, this 1.16 degree, it is falling down. That is the meaning of downwards. Now the third case is value of Cm naught W of the aircraft. So Cm naught W is what? It is the coefficient of movement at 0 degree angle of attack for the wing. Means at 0 angle of attack, what will be the coefficient of movement of the aircraft? So we know the formula that Cm naught W is equal to Cm AC plus CL naught W XCG minus XAC. So here XCG and XAC both are in the same place. XCG is equal to XAC. So this value here both are same. So this will be 0. So Cm naught W is equal to Cm AC. It is given minus 0.1 plus CL 0 W, CL naught W, and here 0. So only this. So you will get Cm naught W is equal to 0.1. Now we have to find out the Cm naught of the total aircraft. So here Cm naught of fuselage is 0. So Cm naught is equal to Cm naught of the wing plus Cm naught of the fuselage plus Cm naught of the tail. So Cm naught of the wing, we have already calculated that Cm naught of the wing here is 0.1. So here we got the 0.1. This is Cm naught of the wing. Now we have to find out Cm naught of the tail. This Cm naught of the tail is equal to neta VH CL alpha T epsilon naught plus IW minus IT. So we have calculated this. We have calculated this. This is given in the problem. This is given in the problem. Neta is also in the problem. This is also problem. This is also. Everything is given. So just put this value. Neta is equal to 0.8. VH is equal to 0.45. CL alpha T is 4.584. And epsilon naught we have calculated 1.16. This is very important here. We have to convert in degree. Otherwise, your answer will be wrong. Okay, because these two are given in degree. So this thing also should be in degree. So 1.16 plus 3 minus, this is given minus 2 into pi by 180. So it is again converted here to the radian. So here 1.6502 into 6.16 into pi by 180, we will get 0.1774. So this we got by tail. But we know that Cm naught for the total aircraft is equal to Cm naught plus Cm naught of the wing plus Cm naught of the tail. So this Cm naught we have already calculated minus 0.1, and here we got from here we got here this one. So net we have got the coefficient of movement at 0 angle of attack is 0.0774. So this we have find out that at 0 angle of attack what is the coefficient of movement. So it is here, it is showing the positive. So it shows that this is the positive 0.0774. This is the positive. It means it is very good for our aircraft. We want for design the Cm naught should be positive. So this is required and it is good for aircraft to design. So being an aeronautical engineer, we should ensure that Cm naught should be positive. And here we are getting the positive. It means your design is perfect. Whatever parameters are given here, they are suiting for the particular aircraft that it is a longitudinal stable aircraft. Now we have to find out the value of Cm delta E. This Cm delta E is dCm by delta T in per radian. We have to find out. So here we know that Cm delta T is also known as a control power, and this Cm delta E is equal to minus Cl alpha T Vh neta T and tau. Tau is given 0.4, neta T is given 0.8, Vh is 0.45, and minus Cl alpha is given 4.584. So you will get here minus 0.660, and this is the Cm delta E. So this is the negative. So control power, it means we have to apply negative delta E to make the aircraft stable. Now we have to find out the next is finding the static margin. So what is the static margin? If you see here, this is the CG and this is the neutral point. So the distance between, this is the XNP and this is the XCG. So this is called, from here to here is static margin, and this is equal to XNP minus XCG. This is called the static margin, and static margin is very important parameter to understand that whether the aircraft is stable or not. Okay, so here static margin XNP minus XCG. XNP is given 0.52, XCG is given 0.3, and we got 0.22. So static margin, this is 0.22. 0.22 means what? It is 22% of the chord line. So 22% of the chord is the static margin, means in this only your CG can move to have the aircraft longitudinal stable. If this CG is moving behind, this is the nose and this is the tail. So if this CG is moving up to here, these are the stable. But as you cross this NP, it become unstable, and this is the neutral stable. So the neutral point is the point in which if the CG reaches, aircraft will become neutral stable. And if it is going beyond the neutral point, then aircraft will become unstable. So that is the effect of the movement of the center of gravity. Now next, we have to find out that the elevator deflection, that is delta E, required to trim the aircraft during cruise flight. So how much delta E is required in this given condition so that aircraft can be trimmed? Trimmed means there should not be any residual forces and the moments. The moment and force, the aircraft is flying very smoothly, no moment, no extra forces, it is smoothly in cruise, it is flying in the same height. We know that the delta E required is equal to minus Cm naught by Cm delta E plus minus dCm by dCl divided by Cm delta E into CL trim. This is the equation which we have to use to find out the how much elevator deflection is required. Here given Cm naught is given 0.0774, Cm delta E is given 0.660. We have find out this. Sm just now we have find out minus 0.22. So if we put this all value in this equation, you will get delta E required is equal to minus 0.0774 divided by 0.660 plus, here is the minus the value is given 0.22 divided by minus 0.660 into 0.569. This all value we have find out already, okay, in the previous answers. So here we got the delta E required in radian. Again we have to see the radian will not give much feeling, but if you convert this thing in degrees, you will understand that how much we have to deflect. Okay, so we got here minus 0.0723 radian and multiplied by 57.3. This become in degrees. So you will get minus 4.143 degree. So this minus indicate that if this is the horizontal tail, this is the elevator, this is called the minus delta E. If it is upward, so it means you have to deflect your aircraft elevator upward minus 4.143 so that your aircraft will be trimmed. So if you are the pilot or you are flying the aircraft and you want to trim in this given condition, you should make your elevator upward minus 4.143. So this type of problem will give you lot of benefits, and as the student or the designers of aeronautical engineer, it is very much essential that you should understand that your aircraft should be statically stable, your aircraft should be trimmed. So like this numerical problems will be giving a lot of ideas to design your wing, to design your tail, to design your body, and make sure that your moments, your forces are maintained in a given condition. So in this, I am thanking you, and I will be very grateful if you can see my all the lectures. It will be very useful for your career, for your examinations, and for your other competitive examinations. It will be very useful. Thank you very much for joining the class.
Like, share and subscribe. Hit the bell icon for more updates.